Hey everyone, thanks for joining me on PostGIS Day. So a little bit about myself. My name is Dennis Boachie. I'm a geospatial software engineer and I'm part of a research team at the Kwame Nkrumah University of Science and Technology in Ghana. I'm also with Hopster, which is a confidence building app and company. Be sure to check us out at hopster.com. Alright, so today I'm going to be sharing with you a bit about graphs, routing, and why PostGIS is a great tool for that, right? By the end, you should be able to convert basic data points into a routing application. Alright, let's get into it.
Okay, so let's dive into it. So what is PostGIS? Well, PostGIS is a spatial database extender for PostgreSQL. It's essentially an extension of PostgreSQL, turning it into a spatial database that allows us to store, retrieve, and analyze geographic data. So it is powerful for applications needing location-based services like mapping, routing, visualization, or any type of spatial data analysis. So why PostGIS? Well, one reason is its efficiency. It's able to handle large spatial data sets exceptionally well, which is critical for mapping applications where performance is non-negotiable. So for routing applications where you might have to run complex queries across a network of locations, this speed and flexibility can make a very huge difference. So to bring this into perspective, let me introduce a use case. Find my classroom. This application helps students, staff, and visitors find their way around campus easily, and I built this powered by PostGIS. All right. So when you're building a routing solution, we primarily have two approaches, at least two. One is to rely on pgRouting, which is a tool that is built on top of PostGIS, and second, to build a custom routing solution. All right. So what is pgRouting? pgRouting, like I said, it's a tool that is built on top of PostGIS and it comes packed with pathfinding algorithms ready to go, like Dijkstra's algorithm, A star, etc., which makes it ideal for rapid development. So if you're like the plug and play kind of person, it's a great option. But sometimes you want more control, more flexibility, and maybe a little chaos. Yeah, so that's where custom routing comes in. But you do need a solid grasp of data structures, right? Like graphs. You don't need to know everything about graphs, but just the basics to get you up to speed, right? Yeah, so custom routing can most of the time give us more control, especially for unique needs or some level of optimizations. Yeah, so depending on the complexity and flexibility we need, we can choose either route. And from my personal experience, uh, custom routing is faster than pgRouting, especially on large data sets. All right, so that's it for pgRouting versus custom routing. Now let's walk through how we can build a routing application step by step. So first of all, the data preparation, you prepare and clean the data. Now, how do you source the data? You could digitize off of a satellite image. So what are we looking out for? Campus, pathways, or roads, and points of interest, which are optional. So you could source your data from other secondary sources, right? And second is graph modeling. We build a network or a graph from this data. So this model allows us to represent pathways and intersections accurately. From then we densify our graph, which we will talk about, and then we move on to database design. We design a schema to store our graph and we choose a pathfinding algorithm for our use case. Then finally, we take it to the next step to build a routing application. Okay, so now let's talk about the data. What kind of data do we need for routing? We essentially need roads data, a linear data. Could be roads or pathways in any spatial format, shape files, flat geobaf, GeoJSON, whatever. And points of interest, it is optional. It isn't necessary for a routing application, but it makes it interesting and interactive. And you could have other optional data such as traffic data, elevation, travel time, weather data. This helps in evaluating the metric for the weight. We will talk about that when we get there. Okay, and I have to point this out. You have to watch out for overshoots and undershoots when you're digitizing or when you source your data from some secondary source. You have to carefully inspect the data, make sure that the logical connections are correct, right? So when I say overshoots, this is what I mean. And so this is what you should expect. A is connecting to B, C is also connecting to B, right? A and B share this edge, C and B share this edge. Now, when you come here, when you're digitizing, if you're not careful, you're going to have this scenario where when you're supposed to snap on B, you go a little bit overboard, and so this edge isn't shared by C and B but rather C and B complement, which isn't what we need, what we want. Another scenario is an undershoot where you're supposed to snap on B, but it just doesn't get there yet, just isn't there yet. Now, this could bring about issues, unexpected results in a routing application. Yeah, so you should look out for that. Okay, let's talk about graphs. Now, in routing, we are dealing with graphs. And if you are new to graphs, this isn't the kind of graph we are interested in. This is the kind of graph we are talking about. Now, a graph is basically made up of nodes or vertices and edges or links, right? In the real world, nodes represent intersections or waypoints, and edges represent connections between these nodes or the pathways between these nodes. We also have to we need to consider concepts like weights. Like weights are like distances or travel times that are used to represent the real world movement between these nodes. So weight is just, it's a metric that is used to evaluate the cost of traversing between nodes. In our case, we're just going to use distances for our weights. Euclidean distances, actually, not any other form of distance. Right. We are going to talk about weight in a bit. Now, this is a graph when you think about it, right? This should help you see how graphs apply in the real world. This is merely path data. It's just lines data that I am displaying, and I am just showing the vertices that are in the data. Now we have to model it in a way that the computer can understand and interpret, right? A graph is fairly easy to implement. Once you understand the concept, there are tons of resources out there on graph implementation, right? So you can do that in your favorite programming language, and you can apply it in the routing application. Right, so now let's talk about the weighted graph. We've talked about weights. A graph that is weighted is a weighted graph, right? So the cost of moving between these nodes have been evaluated. If you wanted to move from A to C through B, well, visually you'd see the cost would be 8, which is the sum of 6 and 2. If you wanted to move from A to C, the cost would be obviously 4 through D, the cost of the sum of 2 and 2, right? And I also have to bring up this concept, directed graphs and undirected graphs. Directed graph is a graph where you can only move in one direction from a certain node to some other node. You can only move in one way. And a non-directed graph is where you can move both ways. So in our case, we are using an undirected graph. We want to be able to move both ways. So we can move from A to B. We could also move from B to A, but at the same cost. All right. So now let's talk about dense graph. What is a dense graph? So given A and B, what we do is we segmentize. Yeah, so if you don't want to use the word dense, we essentially use segmentize. By segmentizing, we introduce intermediary nodes between the already existing nodes, and then we have our edges as so. So originally we had the cost of 6 moving from A to B, and now it has been broken down into 2, 2, 2. So A to C, you have a cost of 2, C to D, you have a cost of 2, D to B, you have a cost of 2. And when you look at the original one, we haven't deviated. We've maintained the integrity of the original node to the extent of the node, right? So that's what segmentizing is all about. Now, why do we segmentize, right? In routing, you want your graph to sufficiently reflect the layout of the area you're working on to a very high degree. So when you look at Google Maps, for example, when you make a search query from one location to another, it seems as though the path that is returned, right, it's starting from exactly your location to exactly your destination. But that isn't the case. It's effectively just a mapping between your location and the graph and your destination and the graph on the graph, right? Which brings up a problem that is known as the nearest neighbor problem in computing. We will dive a bit deep into it, but effectively what we want to do is to find the nearest node or vertex to the query point, which in our case is the user's location, as well as the nearest node to the destination. But let's just focus in on just the user's location for now. So given A and B, right, and then our user's location, U, if we wanted to find the nearest node, well, visually, as we can see, it is B, right? And so now what happens is when we get our shortest path starting from B and not U, remember I said it's a mapping between the user's location and the graph. So to wherever the destination might be in the graph, well, this is what it would be. The user would have to walk all the way to B to continue the path. And that is not what we want, right? What we want is something like this. Given A and B, we segmentize A and B, maintaining its integrity. But in this case, computing the nearest neighbor wouldn't be B anymore, but would rather be E, as you can see. And so the user doesn't have to walk all the way to B to continue the path, but rather would have to walk to E to continue the path. And that is what we want. So that is why we segmentize our graph or our edges essentially, just to have a smooth experience in the application. So we're going to trade some space for some smooth routing, right? So in a nutshell, segmentizing breaks a path or a segment into smaller segments, which is crucial for accurate routing. Well, there's a number of ways you could achieve this. You could spend several hours trying to write an algorithm for this, like me. Or well, you could, with PostGIS, in just one line, save yourself of the headache of trying to catch all edge cases, right? So here's an example of an SQL command to segmentize a line, creating additional points along it. Super simple, right? So we just have a select statement, and so let's focus in on the ST segmentize. The first argument is a geometry type, a line string type actually, and then you pass in the interval you want between the nodes you are inserting, right? And then finally as text, and this is the output that we get. Simple, super simple, and that is that. Okay, so if we wanted to visualize, this is how it would look like, and our users wouldn't have to walk to the old nodes that we saw in the previous slides. Okay, so now let's talk about the k nearest node problem, KNN. So now given our graph on the left and our user's location on the right, how do we retrieve the closest point in the graph to this user's location? Well, an intuitive and naive way to do this would be to calculate the distance from the query point, which is the user's location, to every other node in the graph, right? And visually, this is how it would look like. You compare the distance from the U location to every other node in the graph. Now, from an algorithmic perspective, this is incredibly slow when you're dealing with a large data set, right? And this is how you might implement it in a programming language. So this is a small script in Python that is trying to implement that visualization. So first of all, we iterate or loop over all the nodes, compare the Euclidean distance from the user location or the node to every other node in the graph. while keeping track of the smallest distance, right? So once this is over, you simply return the node with the smallest distance to the user's location. Well, this is fine, right, if we have only a few hundred points, but if we have millions of points, that is where the problem arises. This program will be too slow and incredibly inefficient to use in practice. In algorithmic speak, you would call this a linear time solution, which isn't that efficient, right? Now, this is a very important concept. It is very dear to my heart. I talk about it a lot, and you might think, well, who on earth is going to do this? Well, I did find myself in a similar position some time ago. So that was when I realized how important data structures are, right? So how do we combat this? Well, we have to talk about GIST. We can't talk about PostGIS without talking about spatial indexing, right? So this is the secret to making things faster in PostGIS. We do know that performance is key, and this is where spatial indexing comes in. So from the PostGIS manual, it did say that spatial index is one of the 3 key features in a spatial database. So indexes make using a spatial database for searching even large data sets possible, right? So without indexing or without any form of spatial indexing, any search for a node would require a sequential scan, which is what we saw in the previous slides, right? Iterating over all the nodes. So it would require a sequential scan of every node in our graph, right? And so our indexing would speed up the search by organizing the data into a hierarchical search tree, which can be quickly traversed to find the particular node that we need, right? So spatial indices are one of the greatest assets of PostGIS. In the previous scenario, we had to iterate over all nodes to find the nearest node. This can get very costly if we saw that it could get very costly if we had about over 100 million nodes, which means we would have to do 100 million comparisons, and that's what it means. Now with spatial indexing, or with indexes in general, the cost of having to compute the nearest node would be as low as only 20,000 comparison, right? And I won't go down the rabbit hole about the time complexity of spatial indexing, right? But pro tip, you don't index everything just because you can, just because you know you would have a faster access to your data, to whatever you're looking for. You don't have to do that because you can. Your database would be hurt if you did that, right? So now this is indexing with GIST. See, very simple. Create index IDX node geom on node using GIST geom. So on the node table using the GIST. Now what is GIST? GIST is a generalized search tree, right? We are going to talk about that in a bit. So we are still trying to find a way to combat this inefficiency, right? We're still trying to find a way to find the nearest neighbor to our user location. We've already done step 1, which is to create an index on the table using GIST on the geom field. Now, the second step is to use the distance operator, which we are going to do now. And what we are doing is we are selecting the geom from the node table. Now, assuming we have all our nodes in our graph, all our nodes from our graph in a table, this is where the distance operator comes in. Now, the distance operator returns a 2D distance between 2 geometries. Now, when this is used in the order by clause, now this is from the PostGIS manual, it provides an index assisted nearest neighbor result set. What this means is it utilizes the spatial index that we have set on our field, the geometry field, to find the k nearest neighbors. So we're doing order by geom, given the geom field and then the user location. Now this is a parameterized query. And then since we are only interested in the first nearest node, we limit the result to just one row, which is the first nearest node, since it is in ascending order by default, right? So this uses a hierarchical tree, one such as R trees under the hood. KD trees could also be applied in this instance as well. Okay, so this is a bit of a bonus. So if you want to take it to the next step in building an application, a routing applications where you have users making requests, requests coming in, this is how you might want to go about it. So you have an API that would serve as the bridge between your users and then your application, your backend. Would listen for requests, receive route requests, process them, send the responses back to the client, and all that. So it takes the location information and then it goes through that pipeline. We have the PostGIS components, which should be for our efficient storage and querying of our graph data and our points of interest. And then you choose an algorithm like Dijkstra's algorithm or A-star or the by component, right, which will compute the shortest path between the 2 points. And then after, the API would send a request, would send the response back to the client. Okay, so before we end the talk, I want to show you how the app that I built, the routing app, works. So I'm going to switch to that window and okay, so this is the interface. The backend was implemented in Go, the Go programming language, and the front end in React, TypeScript. And the tiles that you see there are being served from a separate Go server. It's a custom implemented tiled map service. Okay, so let's see how it works. So you see the points of interest, the POIs that are rendered on the tiles in clusters, right? So when you zoom in, you realize that the clusters have been spread out to show all the points that are grouped, and then the blue marker that you see there is the live location of the user, of the phone, of the client. You could also have images associated with the points of interest. It makes it fun and interactive. Okay, you could also search for the points of interest and it will be plotted on the tile map. Okay, so this is the side panel where you would key in your location and your destination, right? You could use your live location, or you could manually type a location. And so I want to move from my location to petroleum building. So once I select petroleum building, quickly the path is returned from my location to the petroleum in a matter of milliseconds, right? And the images at the same time are returned, the images associated with the building. Okay, so that is basically how it works. I'm going to pause it now and I'll switch back to the presentation. All right, so this brings us to the end of the talk, and I hope that the walkthrough gave you a clear view of what PostGIS offers for routing. You have seen that it's a very remarkable tool that bridges the gap between database management and GIS. And I hope I made graphs, nodes, and pathfinding algorithms a little less scary. I'll be glad to answer any questions that you have for me. You can also feel free to reach out to me on LinkedIn. The name is Dennis Boachie. Thank you.
Dennis, thank you so much. Oh, there you are. So I was wondering about your routing engine, if you wouldn't mind, like what did you end up writing your routing engine in?
Uh, you mean the language?
Yeah, language.
Yeah. Okay. I used the Go language.
Okay, so you have a little Dijkstra solver inside Go, and it
Yeah. Yeah.
traverses
Yeah.
the edges in the database.
Yeah. So initially, if you have your graph in the database, I hope you can hear me.
Yes, can hear you.
Awesome. Yeah. So if you have your graph in your database at the start of the server, you read the graph data into memory, and
Right.
then yeah. So before it's even listens for requests from users, you already have your graph ready to be traversed by the algorithm. In my case, I use Dijkstra's algorithm, the bidirectional one.
Yeah.
Yeah.
Neat. How long have you been working with PostGIS?
Uh, for 2.5 years.
Lovely. And what brought you to it? Like what caused you to go in and start working?
I think it's probably the program I got enrolled in the university, geomatics engineering.
Yeah.
So in my second year, no, in my final year, I got introduced to it in class, but out of curiosity, I had already gotten into PostGIS about a year ago before my final year. So yeah, I'd say 2.5 years.
Awesome. Is there a reason why you didn't use pgRouting for your application? It's very close in functionality.
Yeah. Yeah, the reason I didn't use pgRouting is I tried it on a larger data set. I was working on London roads, and they had over I think over 1 million nodes and a lot of edges.
Hmm.
So querying a location, querying a routing and making a navigation query would take a lot of seconds for getting the results. So I had to go down the rabbit hole and do it myself.
Yeah, makes sense. That's one of the
Mm.
questions I've long had for pgRouting developers is why there isn't some sort of a caching mode that allows you to hold the graph in memory instead of reconstituting it every time you make a query. Um, is there anything that you found that you think should be improved in PostGIS?
I think PostGIS is great. I haven't found anything that has made me, you know, I just think it's great. There's nothing I'd say that needs to be improved upon for now.
Okay. Well, thank you very much for joining us. There's a few questions for you in the Q&A if you could answer folks' questions, and I hope you can hang around for the rest of PostGIS Day.